Good morning to all of you. Today I am recording the lesson for the day 33. Today we will discuss about the problems on the SF and BM diagrams for the cantilever with point loads and also with UDL. Now I am sharing the screen, the PPT I am sharing. Here, so all these basic details we have already covered in the last classes, and the sign conventions, everything we have covered. Now, so this is the problem for drawing the SRINIVASULU and VM diagram for a cantilever with point load at the free end. So for this also we have drawn the SRINIVASULU and VM diagram. Now for this, the SRINIVASULU diagram is a rectangle, and here the shear force is having a value of W newtons throughout the length, and it is positive. So this is zero line, and we have drawn above the zero line, and this is the bending moment diagram, and here the bending moment is negative. That's why this is the zero line. So we have drawn below the zero line, that is negative, and in this case the maximum bending moment will occur at the fixed end, and here the value is equal to W into L, where W is the load and L is the length, and the bending moment will be zero at the free end. Now we'll take up a problem on the cantilever with point loads, so that we can able to understand the basics in the shear force and bending moment diagrams. When we take this problem, a cantilever beam of 3 meters long carries 2 point loads, 6 kilonewtons load at free end and 4 kilonewtons load at 2 meters from the fixed end. Draw shear force and bending moment diagrams. So this is the problem given for the cantilever with point loads. So in all the cases of the shear force and bending moment diagrams, first of all, with the given data, we should draw the beam. The beam may be a cantilever, or it may be a simply soldered beam, like that. Then we have to show the loads acting on the beam at the respective points as per the given data. So that is called the loading diagram. Then after that, we have to draw the two vertical lines from the two ends of the beam, and also we have to draw the some other vertical lines from the salient points or the important points. So that is the point at which the point load is acting, or the point at which the UDL is starting, UDL is ending, like that. We got the midpoint, some salient points. So from that also we have to draw the vertical lines, and below that then we have to draw one horizontal line. So that is the zero line for the shear force. And if the shear force is having a positive value, we can draw the diagram on the, we have to show that on the above that line, and if it is negative, we have to draw the below that line, and the another horizontal line is for the bending moment. So that is the zero line for the bending moment, and if the bending moment value is positive, so we can show it over that line, that is above the zero line. And if the bending moment value is negative, then we have to show that value on below that zero line. So like that we have to proceed, and for this we'll proceed like this for this problem. Now this is a given problem. So it is a cantilever. So AB is a cantilever beam, and the point A is called as the fixed end, and the point B is called as the free end. So that beam is shown in the green color. So now the total length of the beam as per the problem is 3 meters. The total length of the beam is 3 meters, and it carries the 2-point loads. So one is the 6 kN, and another is the 4 kN. So the 6 kN is acting at the free end. The 6 kN is shown at the free end. Next to the 4 kN is acting at a distance of 2 meters from the fixed end. So it is acting at a distance of 2 meters from the fixed end. So therefore the distance between the 4 kN load and 6 kN load is 1 meter, because the total length of the beam is 3 meters. So like that we can show. So this is called as the loading diagram. So this diagram is called as the loading diagram. Now we have to draw the two vertical lines like this. We have to extend the vertical lines up to here. So from the two ends of the beam, then the two ends are over. The next to the other point is the other important point. The other salient point is here the point where the another point load is acting. So from here also, from the point C also, we have to draw another vertical line like this. Now, so this is the zero line for the shear force. So this is zero line for the shear force, and having some gap, we have to draw. This is the zero line for the bending moment diagram. Okay. Now, first we have to find out the what is the value of the shear force at the point B, at point C, and at point A. And similarly, we have to find out the bending moment at the point B, at point C, and at point A. Then we have to locate those points. Then we have to join all the points. So that will be the shear force and the bending moment diagram. Now coming to the calculations of the shear force. Now, what is the shear force? To find out the shear force is nothing but the all the, if we consider any section. So if we take any section, the section can be considered at any point on the beam. Then the shear force is nothing but the algebraic sum of the forces acting either to the right of the section or to the left of the section. So we should take only one, either to the right or to the left, but not two. So either, so that if you consider either to the right or either to the left, both will be same. Now, first of all, so we know the sign conventions. What is the sign convention? If the downward force acting or the downward load acting to the right of the section is taken to be positive. For the shear force, the downward force acting to the right of the section is taken to be positive. Similarly, the anti-clockwise moment produced by a force to the right of the section is taken to be positive. That means if the clockwise moment to the right of the section will become negative like this. Okay. Now here you see, so to find out the shear force at point B, just I am taking the section just here only. So just exactly at the just a side of point B. If you draw a section, if you take a section at this point exactly, now to the right means only the 6 kN is acting. To the left means, so this is 4 kN is acting downward, and here we also got another load here that we don't know. But so because we need to calculate only one side, so one side load is known. Therefore, so we need not depend on this load to the depth of the section. So if we take a section here, then to the right, so a downward force of 6 kN is acting. So according to the sign convention, the downward force acting to the right is taken to be positive. So therefore, the SF at B is equal to 6 kilonewtons. Now coming to the point C. So when to find out the shear force at the point C, just you have to consider a section exactly that is just to the a point. So we draw a section at point C. We draw a section exactly at this point. Now to the right we got the two forces. So one is the 6 kN and other is the 4 kN. So both are acting downwards. So right of the section to the right of the section and acting downwards will be the positive. So the shear force at point C is equal to 6 is one force and 4 is the other force. So 6 is one point load and 4 is the other point load. So therefore the shear force at point C is equal to 6 plus 4 is equal to 10 kilonewtons. Now coming to the point A. Now if you want, when you wanted to find out the shear force at point A, now you have to take a section exactly at this point, that is just above just the side of the point A. Now here to the left the reaction acting at point A is acting, and to the right again the same forces, the 6 kN is one force, one point load, and 4 kN, that is 4 kN force is the other point load. So these only these two point loads are acting. So therefore here also if we take the right side, that is 6 plus 4, that is equal 10 kilonewton. So the SF, the shear force at point A is also equal to 6 plus 4, 10 kN. So that means here what is happening is at the point B, the SF is equal to 6 kN, and now here because from the point B and C, there is no other load. So the value of the shear force also same. If you take anywhere here, it will remain equal to 6 kN. And exactly at point C, the so up to here already we got a 6 kN, and exactly due to the action of the another point load of 4 kN, the amount of the shear force is equal to 6 kN plus 4 kN, that is 10 kN. So that is what is happening. The shear force acting between the B and C is equal to 6 kN, and exactly at point C the shear force is increasing to 10k, from 6 to 10 kilonewtons. So that is the 4 kN is adding here. So this is 6 kN, this width is indicating, and here this is the 4. The total is 10 kN. Now, and when we see the parts between the C and A, there is no other extra force. Only these two forces are there. There is no new force. So the shear force will remain constant between the points C and A and that is also equal to 10 kN, and exactly at point A also equal to the shear force is equal to 10 kN. So like this, so now we'll see the diagram. So here, if we're coming to the shear force diagram, as I said, so this is the zero line. So the value on this line is 0. Now, what is the shear force at point B? The shear force at point B is equal to plus 6 kilonewtons. So this is the line. So here we have to take a scale, some scale. For example, 1 kilonewton is equal to 1 centimeters. Or if the value is more, 1 kilonewton is equal to 1 millimeters. Like that, we have to take some proportion scale. And here, so 6 kN is equal to some length we have to draw proportional to the 6 kN. Now here the shear force will remain constant between the B and C, and that is equal to 6 kN up to here. So here what is happening is at point C, we are finding another point load. Another point load is acting at point C. The magnitude is equal to 4 kN. So the shear force is suddenly increases from 6 kilonewtons to 10 kilonewtons with an increment of 4 kilonewtons. So now this is the shear force acting at point C is equal to 10 kilonewtons. Now if you see, now at the point A also, what is the shear force? The 10 kN, because there is no other force between the point C and point A. So only with these two forces. So the amount of shear force is equal to 10 kN. So it is a horizontal line between the point C and point A. Now if we join all the things, this is zero line, and this is the 6 kN up to here, and this is step with a 4 kN, and now this is the horizontal line. Then you have to join this 0 point. So this is a rectangle. So this is the one kind of it is a, so because whenever the point OD is acting on the cantilever beam, so it gives the shear force is a, but we will try rectangles with the horizontal lines. So therefore, so these are the, this is the, this white figure is a shear force diagram, and moreover, so the value of the shear force on the beam is above the zero value. Therefore, all the shear force is shown on the above the horizontal line, that is the above zero line. Now coming to the bending moment. So now the BM calculation. Bending moment. What is the bending moment by definition? Bending moment is nothing but the algebraic sum of the moments of all the forces acting to the right of the section or acting to the left of the section. So definitely, so when we take a section, so generally we'll consider the all the forces which are acting to the right of the section. Now coming to the point B, if we take it the exactly point B, here what is happening is, if we take it to the right, that means just if we draw a line just a side of the point B, if we take the right side is only the 6 kN is acting. Now you forget about the left side, because the anything we can take either to the left, we can take we can take either from the right side. So if we take the right side, only 6 kilonewton is acting to the right of the section, but this 6 kilonewton is acting exactly at the point B. Therefore the distance between the 6 kN force and the point B equal to 0. Therefore, the what is the moment? The moment is nothing but the magnitude of the force multiplied by the distance between the force and the point. Here the force and the point both are acting at the same point B. Therefore, that is the distance will be equal to 0. Then the bending moment is equal to 0. So the bending moment acting at point B is equal to 0. Now coming to the point C. Now if we take the exactly point C, so here if we take the to the right side, so only one 6 kN force is acting. Now if we take just as idea here 4 kN also acting, but the 4 kN also exactly acting at point C, and the distance between the 4 kN and C will be 0, and so therefore this force does not cause any movement about the point C. Now the bending moment at point C means we have to take the moments of all the forces about the point C to the right side. So to the right side only the 6 kN is acting, and the distance between the point C and 6 kN, that is the distance between the BC is 1 meter. So 6 kN into 1. So 6 into 1, 6 kilonewton meters. That is the moment. Now coming to the sign convention. So if we take this is a section, so this that means we can fix the beam at the section point. So this is a section point we have taken. If you fix here, this 6 kN force is tending to produce a clockwise movement to the right of the section. So what is that sign for that one? So what is the positive and what is the negative? If a clockwise movement acting to the right of the section is negative, whereas anti-clockwise movement acting to the right is positive. So here, so it is producing a clockwise movement to the right of the section. So it is negative. So therefore, the bending moment at point C, that is BM at point C, is equal to minus into 6 into 1. So this is equal to minus 6 kilonewton meters. That is the bending moment at point C. Now coming to the bending moment at point A. If you take the bending moments at point A, then you have to consider the section exactly at point A. Now, if this is the section, and to the right, this is the portion. To the left, there is no other force. So, to the right means we got two forces. One is the 6 kN, other is the 4 kN. Now we know the distances. The 6 kN is acting at a distance of how much from point A? 2 plus 1, 3 meters. And 4 kN is acting at a distance of 2 meters from the point A. Therefore, now what is the bending moment? Bending moment is nothing but the algebraic sum of the all the forces. Algebraic sum of the moments of all the forces acting to the right of the section. So here now, so the bending moment about point A is equal to what is that? So 6 into 3 meters. So here also here it is, if you fix the beam at point A, so it is causing a clockwise movement. So it is taken to be negative. So 6 into 3. So that is minus 6 into 3. And the another moment is 4 kN and acting at a distance of 2 meters. So this is also acting downwards. So it is causing a clockwise movement to the right of the section. So it is also negative. So minus 4 into 2. So like this. So the bending moment at point A is equal to minus 6 into 3 minus 4 into 2. So this is minus 18 minus 8. So this is equal to minus 26 kilonewton meters. So they are the bending moments that we calculated from the loading diagram. So the bending moment at B is equal to 0, at C is equal to minus 6, and at A is equal to minus 26. So all are 0 and minus matrices. So we have to take So this is zero line we have drawn. So this is the zero line we have drawn, and here, so this is zero line, and here, so we got so this is the how much it is minus 6 point, and this is the minus 26. Now we have to join with a, so this is a zero line, and this is zero value, this is the minus 6 value, and this is the minus 26 values. Now we have draw with a horizon, that is the inclined line, joining all the points. So now this is the line, and this is the horizontal line. Okay, now we have, this is the, what is the amount, so here it is minus 26. So this is the inverted triangle. So this triangle is the shape, and this will represent the bending moment diagram of the given problem. So now here what is happening is, because this is zero line and all the values of the bending moments are negative. So this is zero value, this is minus 6, and this is minus 26. So we got a diagram below the zero line, and this hatched lines diagram will show the bending moment diagram. So in this way, we can draw the shear force and bending moment diagram, and this is the solution for the given problem. So this is the solution for the given problem. So now we will take the another problem. So now this is the cantilever beam with UDL. So for this, first of all, we have to derive the equation, then we will go to the problem. Here, so the SF and BM diagrams for the cantilever with UDL. Now for this, construct a cantilever beam AB having a length L, carries a UDL of W kilonewtons per meter length, and here the end A is the fixed end and end B is the free end. Now this is the section. So section we are taking at this point. So this is the XX, and that is the distance of the X from the free end. Now coming to the, so first of all, we have to construct the SF and BM diagrams. So for this, first of all, we have to find out what is the value of the SF and BM at the silent points, and then here the accordingly we have to identify, locate, and join the line with join the points with the suitable lines. Then the diagram will be the shear force and bending moment diagram. Now here for this, so we have to calculate the shear forces. Now consider this cantilever. For this, the shear force exerted point, we said at the point, if we take the right hand side, there is no other force acting. So therefore, the shear force acting at the point B is equal to 0. Now the shear force at XX, the shear force at X is equal to to the right of this, so this is x point, and to the right it is having a distance of x from this end. So this amount, so the UDL is given W kilonewton per meter length into this is the distance. So W into x is the force. So W into x is the shear force acting at xx, and the general equation for the shear force is equal to W into x, where W is the intensity of loading, intensity of the UDL, that is W Newton per meter length, and into the x, so this is the distance. So W into x is the kilonewtons. So this is the shear force. This is the general equation of the shear force, and because here it is acting downwards, so here it is acting downwards to the right of the section. So it is a positive one. So plus W into x km. Now coming to the other point, that is the fixed end point A. So here very simple, if you take to the right of the section, so this is the shear force. How much W is the intensity of loading, and having a length of L. So W into L, or even we can substitute the x is equal to L in case of the at point A. So therefore the shear force at point A is equal to W into L, WL kilonewtons. So now at point B it is equal to 0, at x is equal to W into x, and at point A it is equal to W into L. So all are positive values. Now, so we have to locate. So this is zero line for the shear force. So at point B it is equal to 0, and at x some value. So here, but x is less than the L. So having the some lesser value, and at point A is equal to W into L. So you have to look at the these 3 points. So this is 0 point, W into x point, and W into L point. Now we have to join these points with a inclined line. So this is a triangle line. A triangular area is the shear force diagram for the given cantilever beam with UDL. Now coming to the bending moment diagram. So for that we have to calculate the bending moment at the important point, that is the point A, point X, and the point B, point X, and point A. So now coming at point A, so here the force acting is 0, and so the moment caused by that force is also equal to 0. Therefore, the bending moment at point B equal to 0. So that is the bending moment at point B is equal to 0. Now coming to the bending moment at this xx. So it is very important. So what is the force acting at xx? The force is equal to W into x. And this W into x is the magnitude of the force. And this magnitude of the force will generally acts at the centroid of this length. So generally it is a lengthwise. So the centroid will be acting at the midpoint. Therefore, this W into x will act at this midpoint. It is distance of x by 2 from B and x by 2 from xx. So exactly it will act at the midpoint. So at this point, it will be acting, the amount of force is equal to W into x. Now, this is x by 2. Now, we have to take the moment. So what is the moment? So Wx is the force, and x by 2 is the moment. X by 2 is the distance between this xx and this force. So the bending moment caused by this force is equal to force into distance. That is equal to W into x is the force, and x by 2 is the force. So W into x into x by 2. And it is causing what type of movement? To the right it is causing a clockwise, so therefore it is negative. So the value of the bending moment at x is equal to W into x is the force, and x by 2 is the distance. So this is equal to Wx square by 2, and it is a negative because it is acting downwards to the, sorry, it is causing a clockwise movement to the right of the section. Therefore, the value of the BM is equal to minus W into x square by 2. However, the minus sign is not shown here, but it is minus W x square by 2 kilonewton meters. So this is general equation. So now we got the general equation for the bending moment, and with this equation we can able to find out the bending moment at any length of the beam by substituting the suitable value of the length in place of x. So here, if you take the bending moment, if you wanted to calculate the bending moment at point A, so point A means what? So here the distance is counted from here. So here it is x. Up to here it is x. So here what is happening? X becomes L. The point A is nothing but the x is equal to L distance. So you have to substitute the L in place of x. So the bending moment is equal to W into L is the force, and L by 2 at WL square by 2. So minus WL square by 2 is the bending moment at that is point A, that is called minus WL square by 2, and causing a clockwise movement to the right of the section. So here, and the other way also, without the general equation. So if you wanted to find out the bending moment at point A, now the total load acting to the right of the A is equal to this, to the total, this load will act. What is total load? W into L is the load, W into L, and it is generally acting at the midpoint of this L. That is, it is acting at a distance of L by 2 from this fixed end. Now the moment becomes W into L into L by 2. So that is called W into L square by 2. But it is causing a what, clockwise movement. Like this, it will rotate. Like this, it will rotate in the clockwise to the right of the section. So it is a negative one. So minus WL square by 2. Now, so this is the zero line that we have drawn for the bending moment diagram. Now the bending moment at point B is equal to 0. This is a point, and the bending moment at x is equal to minus W into x square by 2. So this is a point. So that means minus W into x square by 2. And what is the value of the bending moment at point A? At point A is equal to W into L square minus W into L square by 2. Here the L value is more than the X. Therefore, so this is having some smaller value than this value. Therefore, we have shown it according to the proportions of the bending moment. So we have to take some scale and to the value of that bending moment, we have to take the proportions. So here is some less value, and here it is some more value. So now this is the one point, this is the other point, and this is the other point. Now how to join these points? That is very important, because in the previous case it is a W into X. The general equation is W into X. That means it is a, just like a y is equal to mx, or y is equal to mx plus c. That is the straight line equation. Therefore, so we have joined with a straight line. But here, what is general equation? The general equation is equal to W into x square by 2. So y is equal to some constant into x square. So it is a, if you recall back, it is the equation of a parabola. So second order in the x term. So that represent the parabolic equation. So we have to join these points with a parabolic arrow. So this is one point, this is the other point, and from here to here also other point. So we have to join all these three points with a parabolic curve. So that is very important. So this is the negative area. This will show you the bending moment diagram. So here it is a positive shear force diagram, and here it is a negative shear force negative bending moment diagram. So whereas it has been joined with a inclined line because it is a straight line equation. But here we have to join with a parabolic curve because it is a parabolic equation. That is very important. So now by seeing this shear force and bending moment diagrams, we can easily understand that the shear force is maximum and at point A, and the shear force value is 0 at the free end, and gradually the shear force is increasing from the free end to the fixed end, that is from end B to end A, that is the point B to point A. Now from this bending moment diagram also, here what is happening, the bending moment is gradual. Here the bending moment at point B is equal to 0, and the maximum bending moment will be occurring at the point A, and the bending moment also gradually increasing for the beam from the free end to the fixed end. And so like this, so by just looking into the shear force and the bending moment diagrams, we can able to estimate where the minimum bending moment is occurring, where the maximum bending moment is occurring, where the shear force is 0 or it is changing from positive to negative. Like this, certain important parts we can able to found just by seeing the shear force and bending moment diagrams. So that is advantages. That is one of the advantage of the shear force and bending moment diagrams. Now, so this is the problem on the cantilever with UDL. Now, so we'll try to solve this problem. Now, you, if it is possible, we'll try to work out. You take this problem. A cantilever 1 meter long carries uniformly distributed load of 10 kN per meter over 0.5 meters of its length beyond 0.25 meters from the fixed end. Draw the shear force and bending moment diagrams. Now, as for the given problem, so this is a cantilever. The total length is 1 meter, and it is carrying a UDL over a distance of 0.5 meters, starting from 0.5 meters from the fixed end. So it is starting at 0.25 meters, and so it is acting over a length of 0.5 meters. So it is ending at 0.75 meters from the fixed end, and this is the leftover length. So this is the loading diagram as per the given data. Now we have to find out the SF and BM. We'll draw the shear force and bending moment diagrams. For this, we have to find out the shear forces and bending moments. Then we have to draw the shear force and bending moment diagrams. First of all, we have to draw so we have to vertical lines from the fixed end and also from the free end and also from the salient points, the point C and the point D also. Now this is zero line for the shear force, and this is the zero line for the bending moment. Now coming to the shear force calculations, the shear force at point B is equal to 0 because there is no other force acting at point B. So the shear force at point B is equal to 0, and the shear force at point D also at this point also 0. There is no other force to the right of the section. So at B and D equal to 0. Now the shear force at point C. At point C means at this point. So what is the force to the right? So 10 kN per meter and over a length of 0.5 meters. So 10 into 0.5. So that is 5 kN is the load acting to the right of the C. So at point C is equal to 5 kN. Now coming to the point A. So here also you take the point A. To the right there is no other force except this one. And what is this one? That the total force is 10 kN into 0.5. So here it is because the intensity is given kilonewton per meter. So that is the per meter length. So we have to multiply this the length of the span over which the unit is acting with the intensity. So 10 into 0.5 is 5. So 5 kN. So that means the shear force at point C and at point D also will remain same, and between the 2 points, point C and point A, the shear force will remain constant, and that is equal to 5 kilonewtons. Now, so we got the values of the shear forces at the important points. That is at point B is equal to 0, at point D is equal to 0, and point C is equal to 5 kN, and at point A also equal to 5 kN. So this is the plus values because it is acting downwards to the right of the section. So it is positive value. So here it is equal to 0 value, here also 0 value, and here it is 5, and here also equal to 5. So because here also 0, here also 0. So here there is no shear force acting between the points B and D. So simply this 0 line up to B and D. Now at point C, the value of the shear force is equal to, that is 5 kN, and here also 5 kN. So now here what is the value of shear SF is 0 here, it is 5. So we have to join, because how to join it is the general equation of the UDL is W into X. So with the straight line we have to join. So 0 to 5. And here the same shear force will remain constant. So it is a straight line, that is a straight horizontal line. So this is the diagram for the shear force, and here all the shear force is positive. So that diagram will represent the SFD for the given cantilever. Now we will stop today's lesson at this point, and we will continue the remaining problem in the next class. So thank you all of you.